two announcements today. First, homework 1 is due today, and lab 2 has been posted. And lab I think I posted on Monday, so you actually have like 9 days to finish it. And lab 2 is much easier than lab 1. I'm trying to adjust to that, so you will not be frustrated and still learn something. So lab 2, basically you will learn how to use Wireshark to capture network traffic, and you will look at IP headers and also ICMP headers, point out some interesting field has been changed by each time you do a trace route, something like that. It will be much easier. You don't need to configure anything. So last class we talked about IPSec. So last class we talked about IPSec, overviewed what is IPSec and what is IPSec policy. And this class we're going to see the details of two IPSec protocols. One is called Authentication header, and the other is called ESP. So basically, we learned that there are two modes in IPSec. We have a transport mode, which is used for end-to-end secure communication, and we also have turtle mode, which is usually used for gateway-to-gateway secure communication. And if we are using turtle mode, in most cases we use it for VPN to collect different sites together. And in transport mode, we are adding one IP header, insert one IP header between the original IPSec header, between the original IP header and the IP payload. And in the turtle mode, we are adding one new IP header and a new IPSec header. And the original IP header was not changed, and it is used as the inner IP header. And the gateways will take out this part and forward those original IP packets. So we will first look at authentication header. So authentication header is a member of this IPSec protocol suite. And it can be used in both modes, transport and turtle. And authentication header, AH, it can provide data authentication and integrity. It will use keyed MAC, message authentication code, to provide data authentication and integrity. It can also protect against replay attack. So if the attacker captures some IP packets and trying to send it again, reuse it, it will not work. We will talk about how it works in a moment. But AH doesn't provide protection for confidentiality. It doesn't encrypt the payload. It doesn't encrypt the header. So how AH can actually authenticate and maintain the integrity of this message? It uses keyed message authentication code. We discussed this in the crypto basics. So I will remind you how it works here. So first, this is a symmetric key crypto system. There is no public key. The sender and the receiver, they somehow share a secret key. So at this point, we don't care how they share that key. Maybe they negotiate that key using Diffie-Hellman, or they have another secure channel, offline channel, to transfer that key. But they somehow share this secret key. And when the sender wants to send a message, we denote it as M, and the sender will compute an authenticated tag, which is the key, the shared key, concatenate the message, then put this as an input to a hash function, and we generate a tag. The sender will send the message and the tag together to the receiver, and the receiver can verify if the tag matches this message by doing the same thing. The receiver will use his secret key and generate the tag again to say if the tag matches with the tag he receives. If they match, means only this sender can send this message. And also this message has not been changed during transmission. And any attacker cannot forge this tag without the key. So in this process, the authenticity and the integrity of this message are maintained. So replay attack, how this authentication header tackles with replay attack. Basically, in this header, there is a number called a sequence number. And this sequence number has to be increased to prevent this replay attack. So when there is a threshold, a maximum value for this sequence number negotiated between the sender and the receiver. So whenever the sequence number reaches that maximum value, which means both the receiver and the sender, they have to negotiate new keys. And in IPSec, it's not only new keys, including new keys, new index, and that is called the security association. So if they negotiate a new security association, means they are changing the keys. So even if a previous packet may be captured, later communications, they are using a new key. So this can somehow defeat the replay attack. So we're going to look at some mechanics, how it actually works. First, we will look at the authentication header protocol in the transport mode. So we know that in transport mode, the IPSec header is inserted between the original IP header and the original payload. So this is the new header, what the new header looks like. First, we have the old IP header, but this IP header also has to be modified. So can anyone tell me which field do you think should be modified? This is the old IP header. What field do we have in the IP header? We have source. Checksum has to be, but the reason we update checksum is because we update something else, right? If we didn't update something else, why do we have to update the checksum? So in the IP header, there is a field called protocol, which specifies what is the payload. And if we are using TCP, that protocol field will be 6, which means that the payload is a TCP segment. But here, after the IP header, this is not a TCP header anymore. This is a new header called IPSec header. So actually, that's why this part has to be changed. We need to change the protocol of that IP protocol field. So, and this part, the red part, is the IPSec header. And we can say the first field is the next header, which specifies what is the payload after this IPSec header. In this case, if the payload is a TCP, we will put a TCP 6 here. So the IP header will not be, the payload of the IP header is not a TCP packet. The payload of the IP header is authentication header segment packet. However, the payload of the authentication header is a TCP. And we have this security parameter index. We talk about this number this Monday. So basically, this number is part of that security association. This number is an index of the key the receiver and sender actually are using. So we cannot send the key in plain text here, right? But somehow we have to, the sender has to notify the receiver which key you are supposed to use to decrypt this or to authenticate this. And we also have a sequence number. This is used to defeat the replay attack. And we have the payload. So in the authentication header protocol, all these parts, starting from the original IP header to the payload, they are authenticated use the algorithm we talked before, the keyed message authentication code. So all of them are taken as input and generate one hashed message. and that hash message in the protocol is called integrity check value. And this integrity check value, when the receiver receives it, it will do the same thing, calculate the value to check if they match. If they match, which means this message is from the sender who I negotiated the key with, and also this message has not been changed or tampered in transmission.
Which fields? So do you include the payload?
Yes, this is a payload.
So no, the payload is included in the message?
Yes.
Is that the integrity check value is not included?
No, this value, yes, they were calculated from here, concatenate this part with this part, and it put the integrity check value here. Yes, but there are something else I will talk about.
It does or does not include it? Is it skipping it kind of like the arrows there, or is it?
It will skip this part.
It skips it. Yeah.
Yes, because when you put it here, you don't know what it is, right? Maybe when they actually calculate it, they may fill with all zeros there first, then calculate the values and put it there. Fill it, yeah. So first is the protocol field. This is a changed IP header. We have to change the protocol field. It used to be a TCP number 6 here, TCP. And because now we don't have the TCP header, instead we have an IPSec header, so we need to change to the IPSec protocol. There are two we are using, and this one we are using authentication header protocol. So this part will be changed to 51. And you see that there are some other interesting fields here, like time to leave and the header checksum. Those fields will be updated by the middle boxes. Usually, right? So this field is going to decrease whenever this packet arrives at a router. But in IPSec, especially in the transport mode, we're trying to build an end-to-end secure communication. So, but if the routers, they have to update this part, they are changing our packet. But how can we maintain the integrity of it? So actually, when we calculate this integrity check value, we are only calculating the parts that were not mutate. For example, the security parameter index, the sequence number, the payload, the headers, and also in the IP headers, we will only calculate something like the source IP address, destination IP address. We are not going to calculate the time to leave or checksum part, because those parts, the routers, the middle boxes, the gateways in the transmission paths, they will change those fields. So IPSec cannot really protect those fields. But fortunately, maybe those fields, they cannot be used for a lot of attacks. So we can't afford not protecting those fields. So this integrity check value, like I said, is just a keyed message authentication code. So it will only calculate the parts that do not change, and also upper layer data, which is a payload. And in the specs, so imagine how long would be this message authentication code. We may use MD5, we may use SHA-1. So usually they are like 196 bits or 256 bits. But in the IPSec specs, they don't want to use that full hash value. So they allow you to truncate that hash value, just take maybe first half of it. So usually just 96 bits of it. Any questions so far? So we can also use this authentication header protocol in the turtle mode. So in the turtle mode, two new headers. One is the new IP header, and one is the IPSec header will be added before the original IP packets. So in this case, we still have the next header in the IPSec header. and this one specifies what will be the protocol of the payload. So in this case, the payload part is not a TCP anymore. It's actually an IP packet. The whole thing was the original IP packet. So in this case, we should fill number 4, which means IP packet in IP packet in the next header. And obviously, in this outer IP header, we also have this protocol field, and that field should also be filled as 51 because we are using authentication header protocol. Then in this original IP header, we also have that protocol field, and that one will have number 6 TCP because the payload is TCP. So in this case, in the turtle mode, we are going to calculate the integrity, the hash value of everything except the integrity check value. So in this case, the original IP header, the hash value will be calculated. We don't care if there is a mutable fields or they are not changed. We're calculating all of it. But in that transport layer, we have to skip those mutable fields. The reason for this is because if we are doing a turtle mode, we are sending this from one gateway to another gateway. And all the routers in the communication path, they're not going to look at this field. When they update the TTL field or when they update the checksum field, they are going to update the checksum here, the TTL here. So they're not changing this part. So this part keeps intact during transmission, just from gateway to gateway. This is why it's called a turtle mode. So if we compare the integrity check value in the turtle mode and transport mode, we can say that actually they do the same thing. The outer IP header field the part that do not change, because in this part, the mutable part, when we calculate the hash value, we will also skip that. But in the authentication header protocol, the outer IP header is the original IP header, just changed. We are not adding one header there. And we are going to calculate the integrity value of all the IPSec headers except the integrity field itself, and also all the upper layer data, TCP, or in the turtle mode, the original IP header and the payload will be considered into this calculation. So this is how IPSec compute or maintains the authenticity and integrity. So basically, we are using the keyed MAC code we talked about in the crypto basics. Any questions? So the next protocol we are going to talk about is called EPS. So ESP, sorry. So ESP can provide the data integrity and authentication. But in addition, it can also provide data confidentiality, which means it will use symmetric key crypto to encrypt the payload. So this is a ESP packet in transport mode. So previously, we are adding the authentication header between the IP header and the IP payload. Now we are adding the ESP header instead of the AH header. However, because we are doing encryption, one problem we had in encryption is if we are using symmetric key crypto, we are treating each block. We are encrypting each block individually sometimes. So we have to add some padding there to make the payload is the size of the payload, the multiple of the block size. So there are some paddings we have to add here. And when we add some paddings, we also need to specify what is the length of this padding. And in ESP, we have the original transport node. We have the changed IP header. In this case, the protocol field used to be TCP will be changed to 50, which is ESP. Then this ESP header will specify what is the payload protocol, and in this case it's a TCP, and we still have the parameter index, sequence number, and also initialization vectors. So initialization vector is also another number we talked before. It is used for encryption and decryption. Even though this number is not as important as the key, it should be protected somehow. And we are transmitting it in this packet, and this packet will be encrypted, so not in plain text.
So in order to decrypt, you need that
What?
ID. You need, in order to decrypt,
Yes.
you needed that ID.
Yes. Remember we talked about several operation modes of symmetric key crypto, like blockchain mode, and all those modes you need an initialization vector to start with the first block. So then this part, the original IP payload, in this case, which is a TCP segment with some paddings, can be encrypted using that symmetric key indexed by this parameter index. And then there were another authentication data, which is very similar to the ICV in the AH protocol, but oops, sorry. So they changed the name of it here. They call it authentication data. And this authentication data, they will calculate the hash value from the IPSec header to the end of this payload. So in this case, they are not calculating the IP header, the original IP header's hash value. The reason they are doing this, I'm not sure, but like we discussed on Monday, ESP, since they are not computing the hash value of the original IP header, you can apply ESP first to encrypt this part, to protect the integrity of this part. Then you can apply another layer of authentication header to just protect the integrity and authentication of the IP header part. So the only part is encrypted is TCP, the original TCP segment. So if we compare authentication header protocol and ESP, we can have this figure. This is the original IPv4 packet. We have the original IP header. We have a TCP header and your data. Then in the header authentication transport mode, new authentication header will be inserted here, and the whole package, all the immutable fields, we will authenticate it and maintain the integrity of it by calculating the keyed hash value. And internal mode, a little bit different. We are adding a new IP header or new authentication header, and the whole part we are maintaining its authenticity and integrity. But in this ESP transport mode, we are adding a ESP header, ESP trailer, which is just some padding there, and also ESP authentication field. This field used to be in the AH header, and we encrypt this segment part with this padding, and we only authenticate from the ESP header to the end of this payload. So the difference here is in ESP, we are not authenticating the original IP headers. And in ESP terminal mode, we are adding this new headers first, then encrypt this from the payload, original payload, to the end of this payload. We are not encrypting the header, because if we encrypt the ESP header at the receiver side, they cannot decrypt that, because the index of the keys is specified in this ESP header. then the whole message, except the original or the new IP header, will be authenticated. So if you are using VPN kernel mode to connect to your company's network, so you are using ESP kernel mode, and all your message will be encrypted in this way. But in this case, the new IP header is not protected. That's why they may apply another layer of authentication header here. Any question here?
And if you combine them both, does it do the ESP first and then the AH?
Yes. For the outbound message, you will do ESP first, then AH second. But for the inbound, obviously you need to do AH first, then ESP. Yeah. So IPSec has many advantages. It gives us this secure channel, provide confidentiality, authenticity, and integrity. And it has been widely used to collect sites together, and compare with having a dedicated physical channel. Even let's say that physical channel is secure, this way is much, much cheaper. But still, compared to the original IP, it is computationally heavy, because if you are using ESP, you have to encrypt all the communications. But if you are just using AH, the performance is not bad actually, because you don't need to do encryption or decryption. You are just calculating a hash value. And we talked in crypto basics, calculating hash values is really quick. So IPSec can enable users to work from home and mobile host to have a secure communication with your corporation network. However, IPSec also has many problems. First, which we are going to discuss next week, is you need to somehow share the key. That's why IPSec is not using public key system. It's using symmetric key. So we still need to share the key, and there is a suite of protocols to do key negotiation. Even though some of it is based on Diffie-Hellman, but to actually make it work in reality, you have to change a lot of things. So we're going to discuss that Friday. And IPSec, if there is a single failure in the path, it will disconnect the entire network. And because of you have to do a lot of encryption, decryption, the performance can be bottleneck. And the most interesting thing is IPSec is not compatible with the original network address translation protocol, not a protocol, a mechanism. So we will talk about that in a minute. And also, using IPSec, you are adding some trusted entities there. For example, gateways. If you are using turtle mode, you have to trust those gateways. But what if those gateways are compromised? So everything you believe is safe is actually compromised. So next, we are going to say why IPSec is not compatible with network address translation. So first, what is a network address translation? So we talked IPv4, we don't have enough IP addresses. That's why for everyone to use an IP address, normally we have a router at home, and that we have a private IP address at home. Your computer will have IP address something like 192.168. That is a private IP address. So when it talks with outside, let's say ASU web server, when the web server returns the package to you, the destination address in that package, the return package, cannot be your private IP address, because the public routers, they don't know how to route to your private network. So the reason we have this network translation is to minimize the impact of lack of IP addresses. So all those home routers we are using right now, they use some kind of NAT. And the most popular way to use NAT is translate an IP address to an outside IP address which with a port number. So for example, here we have two computers in your home network, and you have a router. And this router has this network address translation ability. It has an internal IP address, which is the network, the private network, 192.162.0.0. This is a network. And it also has an external IP address starting with 68.40.162.3. So when host B wants to talk with a host on the internet that has a public IP address, host B will use that host's public IP address as the destination IP in the IP packet. And it will use its own IP, this private IP, as the source IP. So when this packet arrives at the router has to translate that packet. Otherwise, if the router will simply forward that, then this public IP, the host C, will think host B's IP address is this. And when it sends back an IP packet, this router in the middle, they don't know how to forward this because there might be millions of hosts that has a private IP address. They don't know how to forward this. So this router has to change the source IP. So how it is going to change that? It will use its own public IP address associated with a port number. So this port number in this scenario is tied with this host, or maybe in some cases it's tied with the host's one process. So when the host C receives this IP packet, the source IP will look like this IP address, 68.40, not this IP. And the destination IP will be host C's IP. So when host C replies this message can be routed by other routers because this is a public IP. Other routers knows how to forward this packet. Eventually, when this packet arrives at this router, your home router, and this home router will see the port number. Oh, this is a port number 5280, and I know this port number is associated with this host. Then it will do a lot of translation to change the destination IP field from this IP to this IP, then forward this package to the host. This is how network translation works. So basically, is it clear? Any question? So why IPSec is not compatible with this? Any high-level idea why IPSec is not compatible with this? What we are trying to achieve in IPSec? We are trying to achieve an end-to-end security in the transport mode, right? But in this case, the source IP address and the destination IP address have to be changed to make it work. So basically, IPSec is designed to prevent something like this, to prevent the middle boxes or attackers in the middle to change the IP address, IP source IP address and destination IP address. So that's why this is a huge problem. So there have been many proposals to solve this problem because we want to use IPSec and we also want to use NAT. So there is a protocol called the NAT traversal. So this protocol defines how we can still use IPSec behind a NAT. So basically, they add another layer here and another UDP layer to encapsulate all the IPSec ESP packets. So this part is very complicated, actually. So we're not going to the details, but basically the principle here is you need to understand why IPSec actually conflicts with NAT. So this new protocol, NAT traversal, will add this new UDP headers to encapsulate all the IPSec packets to make this work. So this is actually a very interesting thing is in network. Every time we find a problem, it seems like hard to solve, we just add a new layer there. We add a new layer, so it's kind of strange. Sometimes we will see more examples later. By adding a new layer there, we can magically solve a lot of problems in network. So this is all I have for today. So Friday, we're going to talk about how they negotiate the keys. That is the only missing part for IPSec now.